All right. So far, what we have done is we have used the inverse transform technique for conceptual continuous distributions such as triangular distribution, continuous uniform, exponential, normal. And we can also generalize this practice for other continuous distributions which have a closed form CDF or at least a table version of that closed form CDF so we can check the inverse CDF. So inverse transform technique is a useful technique. However, sometimes the inverse CDF can be in the form of a closed form formula, or it can be available in the form of a table. Now, in both ways, you can use the inverse transform technique to convert your random numbers into random variates from the specified distribution. Now, what happens if we do not have any distribution? So we have a collection of data, and by looking at this data, we could not fit any probability distribution statistical model for that data, let's just say. So why these kind of cases may happen? So it says there may not be too many observations. For example, you collect data, but the size of the data can be so small. And in that case, you cannot apply a goodness of fit procedure for that data. Therefore, you cannot make a strict conclusion about the statistical model that you would like to use. And another situation is what? Even though you may have lots of data, when you draw the histogram of that data, you would not end up with any well-known conceptual distribution. So it looks like something too weird, and there is not any typical statistical model to use for that collection of data. So in that case, what do we do? If we want to generate an artificial history for that input variable, because we do not have any theoretical distribution or the cumulative distribution function for the data, we can use the empirical distribution. So what is the empirical distribution? Basically, the data itself. The data itself is useful to generate random variate. Again, we are going to use the inverse transform technique to generate from the empirical distribution. Now, how can we generate continuous random variables from a continuous empirical data? First, we are going to use data to find a lower and upper bound for the variable. I'm going to explain how it is going to happen. And then we are going to interpolate the cumulative distribution function between observed data points. Now, the best way to understand this, first going over the algorithm itself, then we are going to show it in practice, and you will realize that in practice it is very easy. So it says determine a logical lower bound and a upper bound for the variable. Now you have so many observations. Now the logical lower bound and the logical upper bound can simply be the minimum of the observations and the maximum of the observations. But in some cases, you can also add an extra logical lower bound and logical upper bound. But once you determine this, we are going to sort all of our observations from x0 to xn. So x0 is my logical lower bound for the observations. X1 is the smallest of my observations. X2 is the second smallest of my observations, so on and so forth. And X capital N here is the largest of my observations, or the logical upper bound itself. So all observations sorted from smallest to largest, and you are also including the logical lower bound and the logical upper bound if they are selected separately from the data. You are sorting them from smallest to largest. Then we generate the random number first. We generate a random number from a pseudo-random number generation algorithm. And by using that random number, we identify index I by multiplying capital N here, starting from 0. Capital N is the total number of values here, the total number of values in the sequence. So you multiply capital N with your random number and you round it up. So you find the minimum integer that is greater than n times r. So these brackets, these weird brackets, mean ceiling operation. Okay, ceiling means what? Rounding it up. Rounding it to the closest integer, which is greater than this value. Now, please be careful about this formula. This means rounding up. So you multiply n with r. Of course, you are going to get some rational number here. Most probably, it is not going to be an integer anyway. Then you are going to round that rational number up to the smallest integer that is greater than or equal to n times r. And then after determining the smallest integer, you are going to choose I minus first index from the above order statistics and ith index, and you are going to apply a shift and scale operation. Now you are going to multiply n with r again, you subtract I and add 1, and then you multiply this value with xi minus 1, then you add it to xi minus 1. This operation is generating a random variate that is distributed between xi and xi minus 1, the ith and the I minus first of these values, by using a uniform approximation between these two values. Therefore, you multiply that scale with n times r minus I plus 1. Now, of course, at this point, if I try to explain this equation, it may not be very possible to understand how this works, but it is always better to learn it in the practice. So let's do that for this small size example, which is from your textbook. Now I'm just going to explain this question in my own language. 5 observations of the 5 crew response times in minutes to alarms have been collected. So imagine now you are going to create a simulation model for a fire station operations. And what is the response time? It's the duration that starts with the alarm going on and it ends when the fire crew reaches to the destination fire incident location. So this is called the response time, and these are 5 observations in the response times to arbitrary locations of fire incidents. So one incident has been responded in 2.76 minutes, another one is responded in 1.83 minutes. Now you see the fire incidents, they grow large in exponential speed. So it takes a very small amount of time for the whole building or a whole room to burn out, unfortunately. So fire incidents are very dangerous incidents. I mean, they require immediate response. So we have 0.80, 1.45, and 1.24 in these 5 different incidents. The response times are collected in minutes, measured in minutes. So we have an insufficient size data, right? So we need to identify a statistical model here, but we cannot do that. We cannot identify it. Why? Because, I mean, you cannot apply any types of goodness of fit test for such small amount of data. So we are going to use the data itself, or in other words, we are going to use the empirical distribution and the following random number sequence. We have 3 random numbers to generate an artificial history for the response times, fire crew response times in the artificial future. So these 3 random numbers will help us to generate response times. Of course, these random numbers are low quality random numbers because of the resolution they have, but we do not want to use any complex value here at this point. Now, how do we start the algorithm? It says, find a logical lower bound and a logical upper bound for the variable. Now, what is a logical lower bound here? You can use the logical lower bound x1 as x0, but technically this is not true. Why? Because does this mean that at least every response time will take 0.80 minutes? Actually, if the fire is just happening in the fire station, in that case, the response time is just going to be, right? So the logical response time, the lower bound for the response time should be 0. Or, for example, the fire incident may just happen in a building which is next to the fire station. So the randomness in the fire response time is coming from the geographic locations of this fire incidents, right? So if it happens just next to the fire station, then the response time will be 0. Therefore, we would like to put a logical lower bound here, and we will say that x0 is equal to 0. Okay, so the lowest response time can be 0. How about the largest one? So we can put a upper bound, the logical upper bound for the observation. So you can say x5 is 2.76, and you can add x6 is equal to 3.5. Okay, for example, the maximum response time is 3.5 minutes, you can say. I mean, how come you can end up with result? I don't know. Maybe you can consider the region of the fire station. I mean, when a fire incident happens, of course, a certain region or a certain district belongs to a fire station, and the regarding district of the fire station can be analyzed, and we can find the maximum distance between any building and the fire station, and based on that we can estimate the maximum response time as a logical upper bound. But at this point in this question, a logical upper bound is used as 2.76, which is the maximum of the observations. So we have a total of 6 data here, and this is the non-decreasing order statistics of these observations, starting from 0, 0.8 is the smallest observation, and 2.76 is the largest. So from smallest to largest, we sorted these 6 observations, including the logical lower bound. All right. So what we are going to do is, in the next step, if we want to convert a random number to the random variate using the empirical distribution, first we need to identify an index, and we are going to use the random number and the order statistics corresponding to that index and the previous index to generate random variate. So let's do that. If you check R1, our first random number is 0.71 here. Okay. So what am I going to do? I am going to multiply 0.71 with n, which is 5 here, right? So this is my logical lower bound, and I have 5 more observations. I'm going to multiply 0.71 with 5. The value becomes 3.55. When it is rounded to top, then it is going to be equal to 4. So this is again called ceiling operation, and this is equal to 4. So what am I going to do? I am just going to apply an interpolation between the third observation and the fourth observation in the order statistics. What are the third and the fourth observations of the order statistics? They are 1.45 and 1.83. So I will write 1.45 in place of x3, and the difference between x4 and x3 will be calculated here. And then I am going to multiply the difference with 5 times 0.71 minus 4 plus 1. And that happens to be equal to 3. Basically, this operation in the last parenthesis is calculating the decimal part of that value, right? So 3.55. So inside of this parenthesis will be equal to 0.55, the decimal part in the interior of n times r. So 5 times 0.75 minus 3 is what? 0.55. Now, what am I doing here? So you see, this is the empirical CDF. Smallest observation is 0 times the logical lower bound. My first observation is 0.80, the smallest. The second smallest is 1.24. The third is 1.45. The fourth is 1.83. And the largest of the observations is 2.76. Since I have 5 observations only, I am just going to consider the cumulative distribution function at the smallest of the observations as 1 over 5. And it is going to be equal to 2 over 5 in the second smallest. It is going to be equal to 3 over 5 in the third smallest, 4 over 5 in the fourth smallest, and 5 over 5 in the largest. So basically, because I have 5 observations here, my CDF is just going to increase with a step of 0.2 at each observation. And in the last observation, it will reach to 1. And I am just going to connect these dots with linear interpolation. So I will just assume there is a linear CDF between these observation points and the cumulative probabilities, okay? Then I'm just going to apply a linear approximation. See that my first random number, 0.75, produces an index equal to 4. 0.75 is between 0.8 and 0.6. It is in the fourth equidistant interval of the random numbers. So this is my fourth interval, right? 1, 2, 3, fourth interval. So basically this operation here is determining the interval here. And we know that 0.71 resides in the fourth interval here. Therefore, we are going to use the fourth linear approximation here. And according to this linear approximation, the inverse is going to be 1.66. It is just going to create an approximation between 1.45 and 1.83. And the second equation here is exactly doing that. So 0.71 minus 0.6 is 0.11, divided by 0.20 is 0.55. Therefore, this random variate must be 55% distant to 1.45 and 45% distant to 1.83. Therefore, what I am doing is I am multiplying this distance of the interval with 0.55 and add it to 1.45, so I find exactly proportional response in this inverse linear function. Now let's practice the second example. Then you can understand better. My second random number is 0.94 and the corresponding interval is the fifth interval. How do we understand that? First of all, 0.94 is between 0.8 and 1. This is the last interval. Or you can use that formula, I is equal to the ceiling of n times r, which is 4.7 in the ceiling operation. That makes it 5. And then I'm going to do my inverse linear transformation operation in the fifth interval. So I'm going to use the fourth and the fifth of the observations to determine the distance of the last interval. And I'm multiplying this with the decimal part of 4.7, which is 0.70. So 0.70 multiplied with this distance and added to 1.83, the produced random variate is approximately 2.48. And finally, in the third example, we have a random number that is equal to 0.12, and 5 times 0.12 is 0.6 rounded up to 1. And the logical lower bound 0 is here. The distance of the first interval in the horizontal projection is 0.80. We multiply 0.80 with the decimal part of the interior of the ceiling operation, which is 0.6. In fact, that value is calculated by n times r minus I plus 1, and I is 1 here, so the value is 0.6. When you multiply 0.6 with 0.8, you get 0.48. So for these three next fire incidents, the response times will respectively be 1.66 minutes, 2.48 minutes, and 0.48 minutes. This is how we generate continuous random variates from empirical distributions when we can never fit a conceptual distribution to the limited amount of data, or we cannot identify any known distribution for the data itself.